Good afternoon, and welcome to the latest Fluid Power World Technology webinar. I'm Mary Gannon, Editor-in-Chief of Fluid Power World, and I'd like to thank you all for attending this talk on hybrid system architectures for on- and off-highway equipment. We would like to thank our presenter, Varun Acharya, for being here today, and for Parker Hannifin for sponsoring this content. Before we begin, let's go over a bit of housekeeping information on the ON24 platform to start us off. On the console, you'll see a number of boxes which can move and resize to suit your preference. If you need technical assistance, use the Help widget at the bottom of your screen or use the Q&A widget to contact us directly. If you have questions for the presenter, please type them into the Q&A widget. We will be answering all questions at the end of the presentation. Thank you again to Parker Hannifin for sponsoring this presentation and for our support of this event. Now, please allow me to introduce you to our presenter today. Varun Acharya is the Electrification Systems Application Engineering Manager at Parker Hannifin. With more than 30 years of experience in motion and control technologies and holding more than 20 patents, Varun brings extensive expertise to his role. He earned a master's degree in mechanical engineering from Oklahoma State University and an MBA in finance from the University of St. Thomas. And now I'm going to turn the microphone over to him. Thanks for being here with us today, Varun.
Thank you very much. Good morning, everybody. Again, like Mary said, I am Varun Acharya with Parker Hannifin, and thank you for joining this webinar. I'm going to talk about hybrid system architectures for on and off highway equipment today, and hopefully give you some novel ideas after this webinar, during this webinar. So let's start with a quick plug on what I am part of. I'm part of an organization called the Parker Electrification Growth Team, and we are based in Elk Grove Village, Illinois, which is about 30 minutes from O'Hare Airport in Chicago. So if you are driving through O'Hare and you would like to visit us, please do give us a call or email. Basically, my team includes, we are a bunch of system engineers, and our knowledge is on hydraulic system, electric machines, and controls. This is where we specialize in. And then we also have some specialists in the team who specializes in certain markets. In our location at Elk Grove, we have a bay where you can bring in a customer vehicle if the customer chooses to. But typically, most of the projects that we work on, the customer don't want to send us their vehicle. But the system we work on is we develop a system solution with a schematic bill of material, and we do some analysis with simulation and before and after. And then if the customer sends the machine or at the customer place, we install the system solution, and then we test it, tune the new system, and then based on that, we give the feedback and then final report with the findings to the customer. And you can see on in the middle of the picture here is our bay where you can work on different machines. We have some test stands as well, some fabrication area, and on the right you can see one of the mini excavator projects that we worked on for electrification, one of the first projects. We had the engine there with the battery strapped on the top. And then we also have a little area in the backyard here where we can dig and do some real work. And we bring in expert operatives to run the machine before and after so we can capture the data as well. So again, the agenda for the talk today is I'm going to start with some electrification trends, some segmentation, some forecast, the challenges, opportunities, if you would. And then I'm going to talk about electric versus hybrid systems in terms of efficiency, performance, and some of the different architecture comparison. So I'm going to show you some system architecture for both a full electric and then compare it with a hybrid. And then the main part would be for the application insights. And this is where we're going to do a deep dive into 3 different examples for hybrid system. And one of them would be for an off-highway backhoe loader example. And then the second would be for a highway, on-highway application, and that would be for a refuse side loader application. And then the final one would be on an aerial bucket truck application. And then I'll conclude with some takeaways and future prospects for hybrids, followed by Q&A. So first thing is electrification is everywhere, you know, so it's in vogue lately. So seems like the secular trend, when you talk to all the people, they're talking about electrification, seems like a lot of push from ESG standpoint. And both our customers and the suppliers, they're looking at electrification from growth standpoint as well. The adoption rate in electrification is different for different markets. Seems like some of them are much more conducive to electrification. And then there is a lot of research work going on into applying electrification to all fields. So one way to determine, you know, what is the best fit for a fully electric equipment or whether electrification applies or not is to look at, you know, the power consumption on the application versus the duty cycle. So to me, that's a very good way to know if electrification is going to make sense for that application or not. So imagine if your power, in this case, in the y-axis and the duty cycle in the x-axis. So if your duty cycle is low and your power required is also low, so electrification makes total sense. So I'm thinking like a golf cart or the consumer mower that we have at home, small forklifts, things like that. So we know that electrification makes total sense there, and it has already happened there. And on the other side, if we look at applications where you have high power and high duty cycle, so I'm thinking like, you know, like a big coach, like a coach bus, big excavator, large excavator, things like that. So in this case, electrification really doesn't make sense, you know, and we don't see that. However, there's an exception. So the exception is in mining. So there are these large infrastructure projects. So imagine you're going to set up a gold mine and you're going to operate that for, say, 15 years or 20 years. And it's in the middle of nowhere. So you have the ability to lay out the electric lines, and it makes sense to have those mining sites fully electrified because you can run this and you can justify it by increasing the productivity, making sure the mining can be operated 24/7, address some of the safety issues and things like that. So high power, high duty cycle. In most cases, we say electrification is not the right fit, but there are some exclusions, if you would. And then there's other two categories, so which is you have the low duty cycle and high power, and high duty cycle and low power. So in both cases, there's a question mark out there. So this is where we're talking about like ag tractors, compact construction equipment, skid steer loaders, things like that. So does electrification make sense or not? I guess in this talk, what I'm going to talk about is I think fully electric may not be the right solution for them, but what I would present to you is a hybrid is a compelling proposition for these cases for electrification. So even though you may not you may not have zero emissions, but you can still help the environment and you can help the efficiencies and things like that. So to me, that's a compelling case to be made for hybrids to be made. And then the other point is the cost goes down as your power and the duty cycle goes down, you know, the requirements. So one way to see, you know, what is the best way to see if a solution is viable long term, you know? So one way to see it is what kind of value do we bring to the end user? So the best way to do that is to look at total cost of ownership. So rather than you know, because one of the big benefits with a battery system is you're paying for the fuel when you buy the battery. So, and also then there are other savings with electrification in terms of maintenance and things like that. So total cost of ownership in the y-axis here captures that. And then on the x-axis, what I have is the year. And just so you know, the source for this data is, this chart is from Caterpillar, and then I made some changes to it. They presented this during an engine summit, diesel progress engine summit a few years back. So basically, the presentation, I mean, what we are showing in this graph is, if you look at low power equipment, so what I mean is less than 75 horsepower, you can see that maybe in the late 20s, you know, so 27 or 28, 2027 beyond, electric is going to make more sense than an IC engine. So for small power, low power equipment, electric would be ready to take off much sooner. However, if you look at high power equipment, when you look at more than 75 horsepower, in that case, the battery technology is just not there. So it's going to take, maybe the projection is beyond 2040s before the electric battery technology, the battery technology can help solve the solution. But the point is, between now and then, the hybrid may be a compelling solution for these kind of applications. And that could help the customer from total cost of ownership. And remember, total cost of ownership takes into account everything, the added cost because of the electric machines that you added, and then provides the value to the customer. So total cost of ownership, if you look from that perspective, from the end customer perspective, hybrid makes sense for them. So now let's look at, you know, why is the fully electric solution not viable for all markets? So if we look at a typical bill of material for this fully electric machines, so what you have is, on the left is the motors, inverters, you know, the battery package I'm showing, VCU, and on the right I'm showcasing the hydraulic system, which kind of stays similar, or at least similar components. But efficiency is an issue, so you have to redo the hydraulic system properly to make sure you use it properly. But when you study the bill of material, the main thing is that 80% of the bill of material, the cost, is really from the battery and the BMS package, if you would. So this is for a fully electric machine, 80% of the cost on the BOM is a battery. So as a system engineer, when you try to work on this system, so your focus is how do you utilize this battery? And batteries are very expensive. So not only it's a big portion of the BOM, and the per kilowatt hour, the cost of the battery is very high. So obviously you look at the system efficiency, you start attacking in individual components. So your electric machine, the motor, the inverter efficiency becomes important, and so does the component efficiency. But the biggest opportunity in a off-highway type equipment is and on-highway work equipment is the hydraulic system architecture, because that's where resides a lot of inefficiency that you can address. Another key point is the weight. So the batteries are not only expensive, but they are very heavy. So when you look at when you do the energy density of the battery, both from a gravimetric standpoint and also volume standpoint, you find that they are orders of magnitude lower than a diesel engine. So say compared to diesel, it might be off by 100x in terms of weight. And also in terms of volume, it might be 50x. So what that leads to is, you know, so you have to make a compromise. So if you have a fully electric vehicle, you have to make a compromise with respect to the volume and the weight of the batteries that you're going to carry versus the payload that really pays you to do the work. So again, back to the point, you know, so is fully electric, is that the only solution? So I just showed you that, you know, the batteries have this high cost and also the weight impact. So if you design a system, you know, you make the efficiency as high as possible, you're going to end up, with a 25 to 30%, say, payload reduction. Is that acceptable, And then you have the other benefits you have in terms of the care from the different federal and state level. You have all the incentives and rebates that's available for this BEVs, the fully electric, and hopefully now for the hybrids as well. So how do you balance that? And then the last but not least is what is the opportunity in terms of a marketable solution, which is going to be simple and low cost. And then you also get the green sticker. So the best solution is if you can come up with, help the TCO piece from the end user standpoint. So you have a solution that you can sell, and then you get the green sticker, and hence you get the incentives from the federal and the rebates as well. So the idea is, how do you come up with a solution that's going to satisfy both? So now I'm going to talk about system architecture. So let's look at fully electric platform versus a battery electric platform and see how the architectures could be different. And this is just a generic architecture. So in a fully electric, maybe the solution could be, so in this case, I'm showing you a compact wheel loader, or wheel loader geometry is what I'm showing. So you have a battery pack with a, you have a battery pack with, and then a gearbox. And on the gearbox, I'm showing a pump motor. So here's your electric motor for driving the pump. And then I'm showing a tandem pump with hydraulic 1 and hydraulic 2. And then for traction, you have two separate traction motor with a final drive and brake. So this could be an architecture that you could use for a fully electric platform. The other thing you could do is you could also take advantage of, can I combine some of these things, So like, for example, so for every, like the pump motor, we need a drive for that. And we also need drives for the traction motor, left side and right side. So maybe if we could, the ideal solution could be if we could combine those packages together. So maybe instead of having a left and right traction motor, we have a single motor, and then we make an axle out of that. So maybe an architecture could be simplified with an axle. So now you just have a traction inverter for the traction motor, and then one inverter for the pump motor. And then, of course, the reason I'm showing the gearbox is because you could size the gearbox such that you spin the pump motor at a high enough speed. So you have, say, for example, so your pump motor size could be reduced by a third. So the hydraulics is running at, say, 2,000 RPM, and the pump motor is running at 6,000 RPM, something like that. So that way you size your pump motor size down. And then you could also combine the inverters together and then have some sort of a dual inverter in one packaging. So these are the things you could do with a fully electric platform. So now let's look at it. If we had to do a hydraulic platform, how would that architecture look like? So in that case, what you could do is in a hybrid platform, maybe you can downsize the engine, or maybe you keep the same engine. So it depends on the application and what your goals are. And then you can have a gearbox, and on the gearbox could be mounted a generator, and you run the generator such that you load up the generator so that you run the engine always at the sweet spot. You may or may not have a battery pack, and our recommendation is to have a battery pack so you have some compliance in the system. And then, of course, for the generator, you need an inverter for that. And then the same traction motor could be left and right, so they also need their own inverter. The sizes are different, obviously, because all the power generated by the generator compared to the traction. So you could do some sizing exercise for commonality and things like that. And then the other thing, again, if I could, from packaging standpoint, what could we do separately, to simplify the system? Maybe we can come up with an axle again for the traction. And so now we have only one motor. and then again combine the two inverters together for this dual inverter for the generator and the motor. So at a high level, when we look at this is how we can come up with a fully electric versus a hybrid architecture-wise. So now I'm going to talk about something that within Parker we came up with. So in the prior slide I showed you on the propeller for traction side, going from hydraulic to electromechanical makes total sense. But for the implement side, removing the hydraulics does not make sense, because if you do the analysis with the electromechanical actuators, removing the cylinders, the hydraulic cylinders with the electromechanical actuators, it's not cost effective, and it does not make sense at this time. So the idea is, can we come up with a simple hybrid system for the implement? So this is what we have come up with. So the element for this hybrid electric system is, number one, you have the engine, and then you have a hot shift clutch, the PTO clutch. And this one I'm showing a Chelsea PTO clutch. And then a piston pump with a through drive. And then the back of the piston pump is what we have is our electric motor slash generator, what we call the GVM. And then an inverter to drive this permanent magnet AC or synchronous motor. And then, of course, a DC battery pack. So this is a very simple implement hydraulic hybrid system that you can use this architecture at different applications. And this is what I'm going to talk about now. So the parts of the hybrid architecture were very simple. But what are the different operating modes? So what does it get me? So basically from operations, the first mode that you can run this is with the PTO engaged and your pump is active. You can have the GVM the motor just freewheels. It just goes along with the ride. And now your engine with the clutch is connected to the pump, and your system is just like your current diesel engine, if you would, or any with the IC engine. The next operating mode could be with the PTO clutch engaged, and the pump could be still in standby or at low pressure requirements, so it's still working. But the GVM motor, we can command it to run as a generator. So basically now we run the engine at the sweet spot. And while we are doing that, we're loading the engine, but we're also charging the battery at the same time. The next operating mode could be, again, with the PTO engaged and the pump engaged, but now we're running the pump at very high load. And in this case, the GVM becomes as a motor and is assisting the engine, and it's helping with the rest of the hydraulic system in assist mode. And then the last mode, last but not least, it's a very interesting mode. In this, we disengage the engine completely, and all we have is the hydraulic pump connected to the GVM motor, and we're just running in a fully electric mode. So we have all these 4 different modes that you can run this simple hybrid system. So again, this is the schematic of the hybrid system. So what's the beauty of this? It's number one is the simplicity. All the components that I have discussed here, they're all standard components. There's nothing new. The only key thing different here would be the system control is complex. So, the 4 modes that I talked about, you have to manage those operating modes properly. You have to make sure the transitions are done properly so you don't have a discontinuity when you change modes from one to the other. And again, the system controls have already been developed within Parker, so we already have the software done. And then the other beauty with this system is you can do adaptive controls. With adaptive controls, what I mean is you can electrically assist and you can vary the pump torque on the fly based on, say, the SOC of the battery and the temperature of the electrical unit. So say, for example, what does that mean? If I have an aggressive driver and I can and the controller, the VCU, is noticing that the person is aggressively using the battery, the system, the controls already knows that. It's monitoring the rate the SOC is degrading, and then it can automatically limit the torque allowed to the driver. So basically, you can be on top of the system and prevent the operator from misusing your system. So the point is, on the control side, it's complex, but it also gives you this added benefits that you can do in terms of making the longevity of the system better, and then give added features to the machine. So again, I talked to you about why there's a need for why hybrid makes sense rather than fully electric, and then I showcased to you a simple hybrid architecture that you could use, and then now I'm going to talk about some examples where you could use. So the first example is this hybrid backhoe loader example, and it's using the same concept that I showed you before. So the objective in this case was, the main objective was engine downsizing. So basically, we took the customer gave us the backhoe loader, and the objective was to downsize the engine from 56 kilowatts to 36.9 kilowatt. And the reason for that is when you downsize the engine, not only you save money on the engine, but also in this case, the emission requirements for the to go below 36.9 kilowatt was a lower emission standard, so the customer could save much more money as well. The second requirement for the backhoe loader was you can take the machine into an indoor area, and the requirement was to operate it in this indoor area with the engine off for 30 minutes. It again depends on the size of the battery pack you put in, but the requirement was that they wanted it to run in this low noise and zero emissions requirements for a certain amount of time. And then the government incentives, so based on the discussions between the customers and the officials, that it was still good for the green sticker. And then last but not least, again, the critical requirement was, the customers making so many IC machines, and they wanted to make the same form factor and then offer the same thing for the hybrid. So the objective was, whatever we do to the machine, it has to be with the same form factor. They cannot make changes to the frame of the machine, etc. So this is what we came up with. So you can see the engine at the back, and then the transmission, and you have the clutch at the back. Again, it's exactly the same architecture that I explained to you before, with a Parker P1M pump, the piston pump, 54 cc, with a through drive, with a GVM motor inverter. And right close to below the operator is where we had the battery pack. The battery pack we selected in this case was a 10 kilowatt hour battery pack. And then to take some more cost out, we were using the cooling system. We were using the return fluid from the hydraulic system to cool the motor. And for the inverter, we were using just fans, and it was installed in the cab in this example. So this is kind of what the system looked like. It's a spring-applied hydraulic release clutch, and then on the back was the P1M 54 cc pump. The only thing with the pump, the controls were, the reason we selected the P1M pump was we had the load sense controls with the electric displacement control on top of it. So basically, the EDC allows us to manage the torque on the fly, irrespective of the load sense command. And the GVM motor / generator at the back is the GVM 210-150 motor. And then we came up with some unique algorithms. One is what we call the battery saver algorithm, and then the other is called the hush algorithm. So one is to make sure you can command the displacement of the pump and also the speed of the servo motor at the sweet spot so you get the maximum efficiency. And then we came up with the hush algorithm, because if you're running in a fully electric mode with the engine off, you want to make sure that you can sacrifice some efficiency, but you want the noise to be as low as possible. And in terms of the hydraulic schematic, I'm not showing the whole schematic for the backhoe loader because it won't be legible in this presentation. But the concept was, the unique concept here was we were using what we call a VFO system. This is called variable flow open center system. So basically the valve is an open center valve, and then the inlet section of the valve has some modifications such that you always have about 0.25 GPM flow going through the open center galley. And then the idea is when the customer strokes the spool, depending on whatever function they select, you restrict the open center galley, and then you command the pump to a higher pressure setting. So the more you stroke the spool, the higher the pressure setting you command. And then if you completely stroke the spool, you connect P to the LS side, and now your pump chases LS and it goes to the highest possible pressure setting, or highest displacement, if you would. And in terms of the pump, like I said, it has a load sense control, but we also have the electric displacement control on top. So basically, you can impose with the VCU on top of what the LS command is. I can command the torque or limit the max torque that's available from the pump with my VCU. Another key difference is we also added a pressure transducer at the pump outlet. So that way I'm monitoring what my implement function pressures are. So that way I know what's my, so that way I can monitor whether my system is, what kind of system demand I have. So these were the findings, if you would, for this hybrid backhoe loader. We worked on this project, typically 3 to 4 months is what it took us. A lot of qualification and a lot of time coming up with really the software. And now that we have the software, we can reuse it for this application and other application as well. So the key thing we came up with was what we call a hybrid productivity factor. So basically, it's a slider that we came up with. And basically, you can, we found out, the requirements could be conflicting. So depending on which part of the world you're running this machine, maybe in some cases, the fuel efficiency is more important. So you may want to run it in eco mode. But in other cases, because the cost of the operator is much more, productivity becomes even more. So then you can run it in a power mode, or you can just use the slider. You can come up with a hybrid value, whatever that is. So basically, you have the ability to either move the slider and go to 100% power mode, or 100% eco mode, or something in between. And based on the testing, and then of course, once we finished the, first thing is like I talked about, we installed everything in the vehicle, and then came up with the controls, and then we brought in the expert operator to drive the machine, and we did before and after testing. And for the same productivity, the main findings that I can show you is for the same productivity, the fuel consumption was 10 to 15% compared to the original machine. And then, like I said, the operator adjustable hybrid power factor, that was the main finding. So depending on the application, you can select whether productivity is more important to you or fuel efficiency. And then the other thing we did is when you are running the machine in a loader mode, so because we're capturing also the engine data, so if the engine starts drooping, then we can always back off the torque from the implement side, and we provide more power to the transmission, if you would. So that was the other thing we did on the loader side. So this is my example one, if you would. And the second example is we worked on a hybrid refuse truck. This is a side loader. And basically a side loader is, imagine a refuse truck with the arm on the side. And the arm on the side is used for pick of the can, as shown in the picture here. And then the other requirement besides operating the arm is a body function. So this is where you have a packer or a compactor, which is compacting the garbage that you have put in there, so the density is proper and you can fill up the refuse truck with the proper amount of garbage, if you would. And typically when they run this side loader, they run it at idle condition, so imagine the refuse truck stopped in front of your house, and at idle condition, then the arm comes in, picks up the can, and then dumps it on the top. And to run this unit at idle speeds, 750 RPM, you need the pump displacement size to be very high. So typically 140 cc, 130 to 150 cc is the pump size, and all you need is 30 GPM. So because of this requirement where you have to run it at very low idle speed, you end up having a very high installed power. So you have 140 kilowatt installed power when all you need is 40 kilowatt to run the functions. And then the other key point is, like I'm showing in the graph here, when you operate the unit at this low speed and high torque, it's very, very inefficient. The CNG engine that they typically use is very inefficient. So this example, having a hybrid is to attack not only optimizing the operation of the engine, it's also the hydraulics downsizing is the big advantage with that. So in this case, the schematic is very similar to what I showed you. We have a hot ship PTO with a P1M, and in this case, we are using a 65 cc. So you can this hot ship PTO, you can engage and disengage, and when you disengage it, you can run the system in a fully electric mode. And then for the arm functions, we have a manifold. And for the packer function, we have an open center valve. The GVM we used is a 210-100 in this case, with an inverter and a small battery pack. And the battery pack in this case, from our analysis, all you need is 10 kilowatt hour, 10, 12 kilowatt hour to meet the requirement. So of course, it depends on the duty cycle of the application. But we figured 10 to 15 kilowatt hour is going to meet the requirements for most of the typical side loader applications. So again, when you come in front of the house to pick up the can, you disengage the hot ship PTO and you run the unit in a fully electric mode. Basically now you are decoupled from the engine. So rather than running at 750 RPM, I can run it at 1800 or 2000 RPM. And because of that, I can downsize my hydraulics. And when I move from, when I start moving the truck, so basically now my engine speed goes up. And in that case, I engage the PTO. And this is when we're running the unit at a hybrid mode. And I start, depending on the load, I can start charging my batteries again. And then also using the packer function at that time. So again, based on that, you can downsize the engine from 140 cc to 65 cc. And it's not just the pump downsizing. Remember, everything downstream of the pump, it gets resized now for this, half the size, if you would. And the battery is just acting as a buffer. Like I said, you need about 10 to 15 kilowatt hour. And the weight of the battery pack is only 100 kilograms. So basically what that does is it allows you the payload, which is in this case refuse. So the truck is to carry refuse rather than carrying batteries. And that's what this allows you to do. So for the duty cycle analysis, sorry, I'm not going to go into the details because it's not barely legible here. But there is a paper written by You can Google my name. I think it's in Waste 360. Myself and my colleague Germano Franzoni wrote this. But the explanation is there. But basically what I want to point out here is you can see the engine speed right now is when you approach the can, if you would, and then you declutch. So right now you're running full electric mode here, and you are creating the flow to run the arm functions. And then C is when you are running it in a hybrid mode with the engine running and the clutch engaged. And you can see, and then the other point here is look at the current. So when you have a positive current, that means you are discharging the batteries. And when you have negative current, so you can see when we're in the C phase, basically we're in the hybrid mode with the clutch engaged. And in this case, I'm charging my battery. And the battery, the beauty is the battery state of charge is always between 40 to 80%. So now the life of the battery extends forever, for a long time, if you would. So again, I showed you the same simple hybrid technique with the existing components and a small battery pack, how you can address an off-highway equipment, which is a backhoe loader, and also a on-highway refuse truck. So now I want to show you, what are some of the other things you could do if the OEM still wants to offer a fully electric vehicle for whatever reason. We have solutions for either or. So one thing I want to point out is what we call the ePTO. This is an electric PTO. So if you have, basically what it means is if you have an electric machine, and then all you have is batteries connected, so how are you going to offer a PTO where they can mount hydraulics to do real work? And so this is where we come up with this ePTO. And the solution is, we say two solutions. One is a modular solution, another is an integrated solution. The modular solution is basically a box that you can mount on the chassis of the vehicle. And it has a motor which is scalable, and an inverter, and also the cooling package. You can kind of see the cooling package and the coolant pump. Everything is built in with a small VCU in there. You can mount a P1M pump with a low noise helicoidal pump at the back. So there's different ways to attack different problems with the solution. And then, of course, if space becomes an issue, the beauty with the Chelsea integrated solution is you also have a gear reduction at the back. So basically what that does is that reduces the size of your electric motor further. And you can run the electric motor at this high speed, and then while your hydraulics is sized for 2,000 or 2,200 RPM. So basically everything is running at the sweet spot, and then everything is shrinks down much on the size as well. So now the third example I want to talk about is a hybrid aerial bucket truck. And these are trucks that you see, now that people are suffering from Helen and all. So with the, people can use this bucket truck to position themselves and work on, the power lines or cut the trees and things like that, or work on the signs, things like that. So the solution here I want to talk about is a low voltage ePTO. And what that does is that eliminates the need for engine idle. So basically, once you position the truck, you can run the bucket close to your power lines and whatnot without turning the engine on. So you can turn off the engine completely. The other thing it provides you is no noise. So once your engine is off, it's almost a safety issue with the engine running. The person in the bucket, typically it's a 2 or 3 person job, and the person in the cab, they can talk to each other for safety reasons. Once the engine is off, they can talk to each other, they can hear each other much easier. So safety-wise, a big help. Besides the noise ordinances, you can run these machines beyond 4 p.m. or 5 p.m. And it's also a very efficient system. So I'm going to talk about efficiency, how we address the efficiency in this case. And then I'll also show you a concept where you could ideally use the same battery pack and use that for energy recovery during braking and use that energy for acceleration as well. So on the propel side, what you could do is imagine this aerial truck, and you can brake into the axle, and you can put a traction motor. The motor we have, like the 210 or 310, we can offer with a through drive, and in this case, a 210 with a through drive, with a small inverter at the back, and then a battery pack. And then all you need is connection to the brake and the throttle pedal. And whenever the person hits the brakes, you can convert this motor into a generator, and you start storing the energy into the battery. And then when he hits the throttle pedal, you can discharge that energy from the battery and assist. So you can save some efficiency if you do that. The point is the same battery pack that's used for moving the aerial, the bucket, if you would, to do the work once it reaches the work site, could also be used for saving fuel when you're moving around. So this is kind of what the solution looks like. So the low voltage EPTO solution is like this. So basically, we have a motor which is a NX8 motor in this case. These are air-cooled motors, which is perfectly fine for this application, with a low voltage inverter, all packaged in one, with a very low noise pump. And then all you're doing is with a VCU, you're commanding this system to come live, and the controls we have also developed. So the controls is what I want to talk about. What we came up with here is what's called electric negative flow control. One of the key things in this bucket aerial trucks is you have to, most of these machines are not EH. You cannot have EH because you are working close to high voltage system. So they are either manual or hydraulic pilot. So that's why you need to have, to address that, this is where we came up with this electric negative flow control idea. So the concept is, the one thing you could do is you can run this e-pump at a fixed speed, and you always create the flow, but it's very inefficient. So what we came up with is a system where you have an unloader. So I'm showcasing here with a closed center valve, with an unloader, and this all can be packaged together into this low voltage EPTO system. And all we're doing is we're looking at the pressure of the unused flow. So imagine the flow is not demanded by the different functions to run the bucket. So all the flow is going to come out from this unloader, and the PX value is going to be very high. So all you do from control standpoint is you're just looking at the PX value. If the PX value is high, you just command the electric motor to go to a very low speed. And when the pressure starts dropping, because the functions are demanding all the flow, so your PX value is going to start dropping, and then all you do is you start speeding up the motor. So it's a very simple controls concept that you can use. And you can do the same thing with open center valve as well. Again, open center, manual or hydraulic pilot. Bucket truck is just an example. You could do it with other examples. You have simple truck systems where you need open center system. You could use the same concept. And basically, you need power beyond on the outlet, and you just measure the pressure. And based on this pressure signal, you just command this electric motor at different speed. So what does it do? Basically, what it does is, if you had a typical open center system, you're going to create this 10 or 11 gallon system all the time. But in our case, since we have the ability to just monitor the pressure, and based on that, we command the speed to go up and down, our losses are very minimal. So you can see when I'm in standby, my losses are less than 2 GPM. So that's the only flow I develop. And the reason I'm doing that is to maintain. I'm running at 500 RPM because I need to maintain some flow to provide the flow to the hydrostatic bearing in the pump. And then as the pressure goes up, because the different functions are being used in the bucket truck, the pressure starts drooping on the PX, on the pressure that I'm monitoring. And you can see the motor speed goes up and the output flow developed from the servo motor goes up. And as you're using all the flow, your losses are almost nothing. So this is a simple negative flow control concept, but the beauty with this is it's a simple lookup table. You don't need a PID loop, and if you are working on a high voltage line, you don't want to have too many gains to play with. The simpler the system, the better it is. So those are my 3 examples, if you would. Now I'm going to conclude with the takeaways, if you would. So basically, I showed you, electrification, the current state, if you would, with the different platforms. We talked about what are the things that really impacts cost, and then, the main thing we talked about is this 3 different examples. I showed you a simple hybrid architecture concept for the implement system. And it's all using standard components. And the key is the software, and the software development is already done. I showed you the example of the backhoe loader, which was an engine downsizing example with the fuel consumption optimization. And then we talked about the side loader example, which was a hydraulics downsizing and also running the engine at the sweet spot. So again, the beauty with the hybrid system compared to a fully electric, when weight becomes an issue, when payload is important, and long range, this drives up cost, things like that. This is where hybrid makes a lot of sense. Some of the headwinds we have is the perception. So the perception is fully electric is the way to go, and then there's a lot of government subsidies for fully electric machines. We need to convince the people that they need to give the green sticker status to the hybrid machines as well. So the headwinds is obviously the subsidies that's currently available to fully electric, this is this free money. But the problem becomes when you really study from a total cost of ownership, even though the idea of having fully electric, zero emission sounds beautiful, but when you actually run the numbers, in our opinion, that hybrid makes a lot of sense. So we think that's the time for hybrid is coming. And if you have applications, please reach out to us, and we would love to work with you on that. And here's the link if you want. There's more Parker components. Information is there. And here's my business card. Please feel free to reach out if you have applications. Our team would love to work with you. And now I'm ready to take questions.
Thank you so much, Varun. That was a great presentation, and I love that graphic at the end. It made me giggle. So we'll get started with some questions. We actually already have quite a few good ones in here that came in pretty quickly at the start here. So I'm going to start with one that came in kind of right at the start of the presentation about fluid losses. Can you clarify, that's not the question, there it is, where it is. Internal fluid losses can result in increased fuel consumption in IC engines. How are those same losses quantified in an all-electric system? And by that, the answer, or the question, is kind of talking about slippage and worn control valves causing pressure losses. So can you kind of address that a little bit?
Yes. So, in an implement system, hydraulics is a mature industry, to be honest. So the hydraulic component efficiency matters, but it's 1 or 2% differences, if you would. The biggest opportunity in hydraulics is the hydraulic system architecture. So what I mean by that, it's not that the hydraulic systems engineers don't know how to make an efficient system. It's just that before, having a single pump and then having a valve that throttles different function requirements, that made a lot of sense. So, but now, because of the, cost of the fuel, it doesn't justify adding additional hydraulic components. So to me, the biggest way to address, the overproduction of flow or the throttling losses, like the person is asking, is by addressing it from a hydraulic system level. So to me, coming up with a new system that you could use with the IC engine. So I know you're going to add a little cost on your hydraulic system, but then having the same system both for ICE and hybrid or electric, that is the right solution in my mind.
Great. I know we're getting kind of close to the hour, so I'm going to ask a couple more questions of you from our audience here. Is there an advantage to having the GVM after the pump versus before the pump, or does it make any difference?
It doesn't. So you could have it either way. But if you had the GVM before the pump, then you need a GVM with a through drive. So that adds cost. So since we already make a pump with a through drive, and we didn't want to add that additional cost in this case, so that's why we went with that architecture. But it doesn't make any difference.
What are the challenges in changing the backhoe loader example to allow the regeneration of energy through the hydraulic pump when the load is being loaded, for example? A lot of these are coming from the same people too, it seems like.
Yeah, that's a very good question. So we have done a lot of studies in terms of the energy recovery piece. And I guess what we found is the additional complication that you do by trying to recover the energy with a boom down, because the problem is the flow and pressure levels are very different when you have boom down and you want to capture the energy. It does not justify adding the additional cost. So of course it depends on the application. So if you have a reach stacker or container handler that you are always unloading containers from a ship, then it makes sense. But in an application where you have a construction wheel loader or a backhoe loader, from our experience and the testing that we have done, we don't think it justifies trying to recover that energy. But it's always possible.
Excellent. I think we have time for probably one more question and answer. So I'm going to pick this one. Do you ever see a delay from when you move the lever to when the hydraulic motor starts to increase speed, or is it a very quick motion?
Compared to an engine, an electric motor is so fast. So really all you have to do is you want to command the electric motor to slow down. So because you don't want to cavitate the unit. So one beauty with if you're using the Parker e-pumps, we have already done testing in terms of the ramp rates. So you don't cavitate the pump. So all those values. So if you're, I would recommend, please go to that website or reach out to us. We can help you select the units. So that way you can do without any issues, So delay is not the issue. You have to slow down the electric motor. That's the answer.
Excellent. Well, I think we're about out of time. So I'm going to cut off the Q&A. But if you do have questions and you're still on, you can still enter them into the Q&A, and Barun can answer them directly to you via email. Thank you, everyone, for attending this webinar from Fluid Power World. And thanks again, Barun and Parker Hannifin, for helping to bring this great information to our audience. We really appreciate it.
Thank you, Barun.
And